So mean value theorem, we're going to discuss the mean value theorem. The code is rightfully the way it is. The mean value theorem is the midwife of calculus. It's not important or glamorous by itself, but often helps in delivering theorems of major significance. All right, so this is actually correct. You'll see later on why that is the case, if not in this course, in future. Okay. So there are few mean value theorems. So first one is Rolle's theorem. So again, it's a mean value theorem, but it is named after Michel Rolle, a French mathematician who lived in 1652 to 1719. So what does it say? It says the following: let f be a continuous function on closed interval ab, and let f be differentiable on open interval ab, and f of a equals to f of b. So suppose you have a function which satisfies the following three things. So let me draw a function like that. So how will a function like that look like? So you have a function. What are the properties your function has? First of all, you have continuous on closed interval AB, differentiable on this, and f of a equals to f of b. So I have f of a and f of b. They must be equal. And what do we have? We have that they are continuous. So let me draw a function. Yeah, this is one example of function. Not every function which is continuous on closed interval AB and differentiable on open interval AB will look like this. But this is an example of one of them. So this is how the function looks like. So in this case, you can see that at some point, what will happen? The derivative of the so the tangent line will become horizontal, or the derivative at that point will become 0. So this is what so there's a point C in AB such that f prime C equals to 0. So this is what Rolle's theorem tells you, right? That f prime C equals to 0 at this C. Yeah. Yeah. So let's go through it again. So f is a continuous function on closed interval AB, f is differentiable, f of a equals to f of b. Then what happens? Then the consequence is, then there's a number. Means what? At least one. There could be more. C in AB such that f prime C equals to 0. Yeah. So let's check if the following functions satisfy the hypothesis of Rolle's theorem. So how do we go about it? First, we need to check, is it continuous on on 0, 1? And the answer is yes. Why? Since x to the half and x to the power 3 by 2 are continuous zero, 1, and hence their difference is continuous. So that's 1. 2, is f differentiable on open interval 0, 1. So compute f prime x. So what is f prime x? F prime x is 1 by 2 root x minus root 3 by 2 x to the power, right? So this has to be an open interval, right? So this is open interval. So this thing is not defined at 0. but this is outside our interval. But 0 is outside because we are looking at the open interval, right? 0 is outside the interval 0, 1. So therefore, the answer is yes, it is differentiable. So therefore, yes, f is differentiable. So to be differentiable, recall, to be differentiable means the derivative exists. To have derivative is same as having, is basically same as saying it is differentiable. F is differentiable on. Now third, what is f of 0? F of 0 is square root of 1. So square root of 0 to the power half minus 0 to the power 3 by 2, which is 0. And that is equal to f of 1, right? Why is that? Because 1 to the power half minus 1 to the power 3 by 2 is also 0. So therefore, all three conditions of all three conditions of Rolle's theorem hold. So there is a value C in 0, 1 such that f of C, f prime C equals to 0. Let's check this problem. So again, we have f of x equals to x to the power minus 2 by 3. And what are we wondering? We are wondering if all the conditions of Rolle's theorem are satisfied. What are conditions of Rolle's theorem? That f is continuous on a closed interval AB, f is differentiable on open interval AB, and f of a equals to f of b. So let's see. So is this satisfied for this function? So clearly this power function is continuous. So f is continuous on minus 1 to 1. What about differentiability? Take f prime x is going to be minus 2 by 3 x to the power minus 2 by 3 minus 1, which is minus 1 by 3. And proper way to see the negative powers is to look at it here. And is not defined at 0, right? So therefore, f is not differentiable on minus 1 to 1, and hence what? Hence we cannot apply Rolle's theorem, since the conditions for Rolle's theorem are not met. Okay, so next one is, it's also a mean value theorem. It's a generalization of Rolle's theorem. Let's see what. So we have f is continuous on a closed interval AB, and f of a equals to f is differentiable on open interval AB. But this third condition from Rolle's condition is missing, right? Rolle's theorem needed the third condition, which is f of a equals to f of b. And in this mean value theorem, you're not asked about that at all. So let's see, what do we get in this case? So we have, so let me draw this scenario. So we have a to b. We have a function. You're not given f of a equals to f of b, so we don't need to draw it like that. And this is an example of a function. Now, so this is satisfying both the conditions, that it's continuous and it's differentiable because there are no sharp corners. Now, what is this guy here? If you look at this guy, this is the slope of the line joining a comma f of a and b comma f of b, right? So let me join this line. So what is the slope of this line? The slope is slope equals to f of b minus f of a over b minus a. Now, what is Rolle's theorem telling you? That there is some point C in between A, B, such that f prime C is equal to f of B minus f of A over B minus A. But what is f prime C? F prime C is a slope of the tangent line, right? So we are saying that somewhere here, there is a point. So somewhere here, there's a point. Let's go slightly up. That at this point, what happens? At this point, these two lines are parallel. So slope of this line is f prime c. So this is what the mean value theorem is, right? So again, let's go through this again. So mean value theorem tells you the following. If you take f, a continuous function on closed interval ab, differentiable function on open interval ab, then there exists a point c in between a and b such that the slope of that point, slope of the tangent line at that point, that is f prime c, is equal to the slope of the secant line passing through a and b. So this is what this is the mean value theorem. So let's see the application of this. So a car is driving along a rural road where the speed is 70 km per hour. At 3 p.m. The odometer reads 8 180 so it's 18,075 kilometers. At 3:18 it reads a 1810, so 18,100 kilometer. Prove that driver violated the speed of between 3 p.m. and 3:18 p.m. Okay. So what do we have? We have at 3 p.m. So 3 p.m. we have speed was what? 18. Sorry, the odometer said 1875 kilometer. And 3:18 p.m. we had what? 18. Okay, so consider the following function then. So you have time function and you have distance. Okay, and let's have this function distance as d of t. And if you look at d prime t, that will give you what? Speed. So what is the distance? So distance is at 3 p.m. is what? 3 comma 8075. And distance at 3:18. See, note the scaling is not proper, but yeah. So generally when you do a scaling like this, you basically draw a zigzag to basically indicate that you have shrunk the axis. And at 3:18, what do we have? We have 3:18 and 18100 kilometer. Now, what is the slope of this line? So your distance will be some function here, right? So this is how distance function is going to be, some kind of function between. So now what is the slope of this line? That is going to be the average speed. So average speed is delta d upon delta t. Yeah, which is going to be what? Which is going to be 18100 minus 18075 divided by 318 minus 3, which is going to be 25 over 18 minutes. But we are measuring what? The distance has to be measured in kilometer per hour. So this can be read as 25 times 18 multiplied by 60, 1 hour 60. That is going to be 250 by 3 kilometer per hour, which is going to be 83.3 kilometer per hour. So now what is happening? Now if we assume distance traveled is a continuous function, it's not an unreasonable assumption, continuous function and differentiable, from 3 p.m. to 3:18 p.m. by mean value theorem, there exists a point C in 3 to 3:18 such that d prime C was what? Was 83.3 kilometer per hour, which is greater than 70, clearly greater than 70 kilometer per hour. Hence what? Hence what? They violated the speed limit. So consider the following function, x to the 4 equals to x plus 1, and we want to show that it has exactly one root. Yeah. So consider the following function then. We'll use the intermediate value theorem to answer partially. Consider the function f of x equals to x to the 4 minus x minus 1 on 1, 2. Now, f prime x, so what we have is f is a polynomial function. Implies f is continuous on, it's actually continuous on whole of real number, but it's continuous, every function which is continuous on all of real number is also continuous on this subinterval. So f is continuous on this. F of 1 is 1 minus 1 minus 1. This minus 1 is less than 0. What about f of 2? F of 2 is 2 to the power 4, which is 16 minus 2 minus 1, so greater than 0. So therefore, what? By intermediate value theorem, f has a at least one real root. Yeah, at least mean it could have many, right? But that's not our goal. Our goal is to show that it has exactly one solution, right? So at least one real root. That is, there exists at least one C. 2, 1, 2, such that f of C equals to 0. Now we want to show that there is exactly one root. Now we need to show that there is exactly one root. Okay, so we will do what is called as, we'll use the proof. We will use a proof by contradiction. So what we'll say is, assume there's more than one root, and then we'll try to come to a which will contradict the hypothesis in some sense. Okay, so assume there is more than one solution. So say A and B. Okay, so then what do we get? Then that is f of A equals to f of B equals to 0. That's one. Also, f is continuous and differentiable on what? On AB. Right? So continuous on closed interval AB and differentiable on AB. Why? Because f is a polynomial function. They are differentiable since f is a polynomial. Yeah. Why? So what about the polynomial? They are differentiable and continuous everywhere. So in particular they are. So therefore by Rolle's theorem, there exists C. Well, there is already C being used here. So let's say there exists D in AB such that f prime D equals to what? 0. So this is what we got using Rolle's theorem. But what is your f of x? Your f of x is x to the 4 minus x minus 1. And what is your f prime x? Your f prime x is 4x cubed minus 1. And if you consider this is always greater than or equal to 3 for all x in 1 to 2. That is for all x belonging to AB as well. So you see at one end you're claiming that it has to be 0, and the other hand you're getting this. So 1 and 2 contradict each other. So 1 and 2 contradict. So our assumption is wrong. So our assumption that there is more than one solution is false. So therefore there is exactly one solution. Okay. So that's one way of looking at it. Another way to look at this problem is look at the derivative. So derivative is positive. So if derivative is positive on 1 to 2, that means derivative is always, so the function is always increasing. If a function is always increasing, it can cut x-axis at most once. Yeah. So if the function is always increasing, right, it may not cut the x-axis, but if it cuts the x-axis, it will cut exactly how many times? Once. So therefore, it has exactly one root. Because we already have shown that there is one root, that means it cuts x-axis, but because the derivative is positive, it can cut x-axis exactly once, right? But this is a more robust, proper way of doing it, right? Now let's look at the following problem. If f prime c is 0 for all x in interval ab, then f must be constant on ab. Now note that you already know one way, right? You already have seen f prime, if f is constant, then we have f prime, what? F prime of x equals to 0. This theorem is other way around. It's saying if the derivative is 0, is the function constant? Yeah. So how do we go about it? So what do you want to show that it's constant? Let x1 and x2 belong to AB. What do we want to show? We want to show that it's constant is equivalent to showing f of x1 equals to f of x2 for all x1, x2 in AB, right? Because then if you show that any two are equal, that means all of them are equal to that same value, right? So, right. So let's apply mean value theorem to f on interval x1 and x2. Yeah. So can we apply it? Yes. F must be continuous and differentiable. Right? F must be continuous and differentiable, and it is continuous and differentiable. Why? Because the derivative is 0. That means the derivative exists. Since f prime x is 0, this implies f is differentiable on AB, but differentiable functions are continuous. This implies f is continuous on AB as well. Yeah, so therefore we can apply, this implies f is continuous on AB, but this implies what? F is continuous on x1, x2, right? Because x1, x2 are inside AB. Since x1 and x2 lie inside AB, right? Okay, so apply mean value theorem. So we get what? Therefore, we have f of x1 or f of x2 minus f of x1 divided by x2 minus x1 equals to f prime c, where c belongs to x1, x2. Yeah. And without loss of generality, let x1 be not x2. So what do we get? But f prime c is 0. right? Why? Because the derivative is given to be 0. So therefore, we get, this implies f of x2 minus f of x1 equals to 0, since x2 minus x1 is not 0, right? Therefore, we can't, this is forcing that this must be 0, or this means f of x1 equals to f of x2. So you have managed to prove the following, that if the derivative of the function is 0 on an interval, then it must be a constant function. Now, another interesting fact, if the f prime x equals to g prime x for all x in AB, then f minus g is constant on AB. That means fx minus gx, fx equals to gx plus c. Yeah. So it's saying that means if two functions have same derivative, they will differ by a constant. So the proof is, again, consequence of the previous one. So let h of x be fx minus g of x on AB. Now consider h prime x, which is going to be f prime x minus g prime x. And because of this part here, this becomes what? 0. So therefore, from previous result, we have h of x is a constant function, right? Because the derivative 0, the function is constant on AB. That is, h of x equals to c. Therefore, we get what? C equals to f of x minus g of x. This implies f of x equals to g of x plus c. So two functions, if their derivatives are equal, then they different, they only differ by a constant. Yeah. So now we can use the following fact to prove the following identity. So prove the identity that arc sine of this is equal to arc tan of this minus pi by 2. In this case, we'll take derivative of arc sine of this and this part, and we show that the derivatives are equal. So let's proceed on that. So first, let's say f of x, let's call this as f of x, and let's call this as g of x. Now, what is f prime x? F prime x is 1 upon square root of 1 x minus 1 upon x plus 1 square multiplied by d by dx of x minus 1 upon x plus 1. So this is going to be 1 by square root of 1 minus x minus 1 upon x plus 1 square multiplied by, what is derivative of this? So x minus 1 upon x plus 1 can be written as x plus 1 minus 2 upon x plus 1, x plus 1. Yeah, so I can directly apply the derivative laws. So what is the derivative of this? So the first one is 1. So this is same as 1 minus 2 upon x plus 1. So what is the derivative in that case? It will be derivative of 1 over x is minus 1 by, so it's going to be plus 2 by x plus 1 square. And that can be simplified further. Bring one of the x plus 1 inside. So we'll have x plus 1 square, x minus 1 square. And then we are left with what? So derivative of this is 1 by 2, right? 1 by 2. Sorry, I missed out that 2. Times 2 upon x plus 1. I send one of the x plus 1 inside. And then you can see that this is going to be 2 This 2 and this 2 will cancel off. So I don't need to write that. I will have x plus 1. And what will the inside simplify to? Inside will simplify to, let's see. So what will be the simplification of the inside part? It will be so the inside part will simplify as now a square minus b square. So it's going to be a plus b, which is going to be square root of x times, when you subtract, you will get 2 so that is going to be x square plus 2x plus 1 minus x square minus, so minus x square plus 2x minus 1. So when you cancel them out, you'll be left with what? 4x. So the answer would be square root of 4x. So which is going to be equal to 1 by 2 square root of x times x plus 1. So, sorry, there is no 2 here, right? Because we are taking derivative of arc sine. So derivative of arc sine of x is 1 upon square root of 1 minus x squared. So this 2 is not there. So this 2 will not get cancelled, sorry. So you will have this 2, and then you will have this 2, and then this 2 and this 2 will cancel, and you'll get a 1 upon 2, 1 upon root x times x plus 1. Okay. So this is a simplification here on this side. Now what is g prime x? So g prime x equals to derivative of this, so 2 times 1 upon 1 plus square root of x the whole square times d by dx of square root of x. So this is going to be 2, 1 plus x multiplied by 1 by 2 root x, which is going to be 1 by 1 plus x times square root of x. So therefore, g prime x or f prime x equals to g prime x. This implies f of x equals to g of x plus c. Now we need to find out c. So we have what? We have arc sine. So if let me write it down. We have sine inverse or arc sine of x minus 1 upon x plus 1 equals to tan inverse of 2 times tan inverse of root x plus c. So now we need to find out the c. So since this is true for all x, we can choose one point for which for one value of x and find c. So let's choose something which we can compute. So let's say, for example, if x equals to 0, then we get what? Then we have sine inverse of minus 1 equals to 2 tan inverse of 0 plus c. But what is sine inverse of minus 1? This implies pi by 2 minus pi by 2 equals to 0 plus c. Therefore, c equals to minus pi by 2. And then when you plug that back in here, you get what you are looking for.